Okay, let's start with the composite area. In this, I mean, let's go back to the basics from the very simple problem what we have here, so that we can truly interpret or understand what is meant by the composite area. Now let's take a look at this very simple figure here. As you can notice, it is composed of different figures or shapes. And when it comes to this, maybe make sure that first you must identify and decompose it into figures, okay? And then after that, you look for the dimensions. You look if all the dimensions are provided. If not, of course, we have to find it. And then next step, we have to find the individual areas of these figures. And once we finish doing that, the final step is to add to find the total area of this whole figure. Okay, so first let's start. Let's assume that these sides here and here are in the same length, of course, and this makes a right triangle of 90 degrees, perfect right triangle. The dimensions we have first is the length of our rectangular shape, which is 10 meters. Its width 6 meters, and then of course, the radius of our semicircle. Let's assume that it is a semicircle. Okay, what we are trying to find here is area, right? So, what is missing here is the base of this base of the right triangle, which is A. We denote it as A. So we can find it by using Pythagorean theorem. Pythagorean theorem. Okay, so denote it as A. So it goes like this: A squared is equals to the length of the hypotenuse 12 squared minus the adjacent side 10. Okay, calculator natin sana yan. 12 squared plus, okay, 44. And then we square it, get the square root of 44, which is 6.6. Okay, now we solve for the area of these two rectangular shape. So area of two triangles, 6.6 times 10, we get 66 meters squared. And then next, area of the rectangle. Area of the rectangle, which is length times width. So get 6 times 10 is equals to 60 meters squared. Okay. So there. Next, the area of our semicircle. Area of semicircle. 1/2 pi r squared. Okay. So we solve for the value. 3.14. Radius niya 3 squared. We get 14.13. Okay, so we total this, we add this, the area of these different figures. So total area, okay, is equals to 66 plus 60 plus 14.13. Okay, we get 140.13 or 140.1 meter squared. Okay, so that is the total area for this whole figure here. Now let's proceed with the parallel axis theorem. Let's begin with this figure here. So we have a block on the other side of a rotating pole weighing 12 kilograms, and on the other side the same block weighing 12 kilograms as well. So both of these blocks is about 4 meters away from the axis of rotation. So first, let's find the inertia of the system. The total inertia of this system is the inertia of every point. So we got the inertia from the first block of 12 kilograms, and we denote it as m1 times r1 squared, and from the other side m2 times r2 squared. So the equation goes like this. Total inertia is equals to m1 times r1 squared plus m2 times r2 squared. So 12 kilograms times the displacement or the distance 4 squared plus r2 m2, which is 12 kilograms times 4 meters squared. So calculate it as, so the total inertia is equals to 384 kilograms times meter squared. So the inertia of the system when the axis of rotation is at the center of the mass is 384 kilogram times meter squared. Now if we move the axis of rotation to the center of the block from the right side, we move it 4 meters to the right. So now identify the new inertia of the system that makes it parallel. So now let's find the new inertia. So the new inertia is equals to m1 times r1 squared plus m2 times r2 squared. So it's equals to 12. The displacement, since it is moved from the right side, the distance now is 8 meters squared plus 12 kilograms times 0. Notice that 0 because it is moved from the center of the block from the right side. Answer would be 768 kilograms times meter squared. That is the new inertia of the system. This is the parallel axis theorem. So it allows us to calculate the new inertia value if we have the original inertia, where the axis of rotation passes through the center of the mass using this equation. So we have the original inertia value, which is the 384. So it is equals to 384 plus 24 times 4 squared. M, which is the mass of the whole system, and D, which is for the displacement of the axis of rotation, and we displace it about 4 meters. So the answer would be 768 kilograms times meter squared. The same with the... Now let's proceed to the center of gravity or centroids. So this problem is not the main concept of centroids, but this might help you visualize the idea of centroids or center of gravity. So from this figure, we have to locate and determine the center of gravity along the x-axis. So let's assume that the fulcrum is at the origin. X is equals to 0. Since the moment is mass times distance, from this side, moment is equals to 54 kilograms times meter. Then from this side, moment is equals to 84 kilogram times meter. Now, to find the location of the center of gravity, we need to take about the moment of the origin and divide it by the mass of the system. So the moment about the origin is gonna be the moment of each mass. Let's denote it as M1 is equals to 9 kilograms, M2 12 kilograms, x sub 1 6 meters, and x sub 2 negative 7 since it is on the left side. Okay, now let's use this formula to determine the point of the center of the gravity along the x-axis. So let's solve. It's equals to M1 9 times 6 plus 12 times negative 7 all over 9 plus 12 equals to negative 30, 51. Total result is negative 1.4 meters. So the center of the gravity along the x-axis is at this position here. Okay, where x is equals to negative 1.4. So now we're going to adjust or move the fulcrum 1.4 meters to the left, and now its dimensions are going to change. So notice that the system is balanced. We have moment is equals to 67 kilogram. Same here, 67 kilogram times meter. So this problem is just too basic. Okay, now let's proceed to the product of inertia. So here we have the problem. Determine the product of inertia of the right triangle with respect to the x and y axis. Here we can determine the product of inertia using the direct integration with the parallel axis theorem on vertical differential areas strips. So y is equals to height 1 minus x d dA y dx is equals to height times 1 x over d dx. Next, L is equals to x, YL equals to 1/2 y, 1/2 times height 1 minus x over b. Now integrating di sub x from x is equals to 0 to x is equals to b. So di sub x from x equals to 0 to x is equals to b. I sub 1 limit b dx. So it is equals to plus x cubed dx. Okay, so it's equals to height 4 minus x cubed 3b plus x. So answer would be 1 over 24 base times height. That would be the answer. For the mass moment of inertia, we have this pendulum. Now determine the mass of the moment of inertia of the pendulum about an axis perpendicular to the page and passing through point O. Now for the inertia of the rod, we have the formula. Now let's say rod, we have inertia is equals to 1/2 squared. This is equals to 12, that is 12 times 15 kilograms times 0.45 meters squared. That would be 0.25. Now for the disk, we have inertia is equals to 1/2 squared. That would be 1/2 times 20 times 0.1 squared. Now let's calculate the parallel axis theorem of the rod and disc to get the mass moment of inertia of the pendulum. So the formula cm plus md squared. That is the our formula for the parallel axis theorem. So 0.25 plus 0.225 squared times 15 kilograms. For the disc, that would be equals to 1. For the disc, this would be 0.1 plus 0.55 squared times 20 kilograms. Would be 6.15. So to get the mass moment of inertia of the pendulum, just add this one to this one, the parallel axis theorem of the rod and the disc. So that would be 7.15 kilogram times meter squared. That would be the answer.